In this video, we're going to discuss a little bit about the locations and forms that different elements show up in on planet Earth. Earth is actually composed of several different regions. There's the inner core, there's the mantle, there's the crust. Life exists at the crust. As far as we're aware, nothing can exist down below. Immense pressures, molten rock doesn't seem very conductive to life. Elements, however, change depending on the region. The outer crust has to float on the mantle. It tends to be made of lighter elements that are less dense, and so that material floats on top. The core is made of very dense iron, and heavy elements have sunk down into the planet over its eons. So let's take a look at the elemental distribution that occurs due to these different locations and processes and materials. On this table, we have a chart of elements and their percent by mass in various locations throughout our universe and our planet. Oxygen, vital for life, makes up about 1% of all the mass of the universe. However, it's 50% of the mass of the crust. The crust is actually silicates, silicon dioxides and the like, what we normally think of as rocks around us. Well, these are much less dense than some of the internal rocks that we get down in the mantles, which are often composed of various sulfide-type materials. These tend to be heavier, sulfur instead of oxygen, and a little bit more dense in their construction. So as we get down into the mantle, there's a bit less oxygen. But if we compare it to something like sulfur, we'll find that there's not a lot of it in the crust, but there's more of it down in the mantle. This is a big cause for the differences in densities of these materials. Some elements, however, can be quite wildly different. If we were to look at iron, it makes up very little of the crust, a fairly good amount of the mantle, and almost the entirety of the core. So why is this? Well, iron is one of the major elements of the planet. Our solar system formed after several generations of stars had lived and died. The first generation of stars, there was only hydrogen and helium. They made some of the heavier elements. But when stars die and go through nova and supernova, at best they tend to make iron. That's the end of the line for the fusion processes. The last stages of the last moments of a giant star's death is when the core starts making iron. This actually consumes energy, cools the star, and turns off the fusion. At that moment, basically the entire core of the star collapses. It no longer has the immense radiation pressure keeping elements pushed out versus gravity. And so the gravity pulls it all in, and in a massive collapse and then rebound shockwave, crushes the core of the star into a tiny little neutron star sometimes, or various white dwarfs, depending on the size of the star and how it died. The rebound blasts the outer layers off, scattering it throughout the solar system, and then eventually throughout the galaxy, to be used by a later star to form. A great deal of the hydrogen in the outer layers of the star was still present, only the core had been fusing and collapsed, so that hydrogen and the other heavy elements it created up to iron spread throughout the universe. Until that had happened, there really wasn't enough heavy elements for planets like ours to form. And so ours had to wait for a few generations of stars to live and die before we could get our elements, but iron tended to be the end of that chain. Elements past iron, we now have good reason to believe, thanks to Virgo and LIGO studies and looking at gravity waves, we've been able to spot a few collisions between neutron stars. And so the biggest, largest stars that don't collapse into a black hole collapse into a neutron star, and when those collide, well, they're made of pure neutrons. As they collide and collapse into a black hole, when two of them meet, they blast out their outer layers. Neutron stars are maybe 20 kilometers across, but weigh the mass of the sun. They're incredibly dense. They spin at hundreds to thousands of times per second, and in that moment of impact and destruction, shatter an enormous amount of material out into space before collapsing to be a black hole. Well, those are just chunks of neutrons, and while they're stable on a giant scale, on a smaller scale, those neutrons start to break down into protons and electrons, and chunks break off bit by bit until small clusters of still neutrons that hadn't broken down yet with protons, stabilize into various atoms. This is how we actually get our gold and our silver and everything past iron. The universe hasn't been around that long, and so there's actually not a whole lot of those later elements, which is why gold and silver are comparatively rare on the planet. Iron is one of the most common late-stage materials caused by those star deaths, and so there was a good deal of it floating around, and it makes up a good chunk of our planet. Because it's so heavy, the original molten planet, as planetary formation began to coalesce and turn into a large solid object, well, it was still molten. That iron drifted around and was pulled by gravity, and it pulled deeper and deeper. The core of our planet is believed to be a solid, giant iron sphere. Due to the enormous pressure, despite being at over 6,000 Kelvin, it's actually easier to be a solid at that pressure than it is to be a liquid. And so the core of the planet is believed to be crystalline iron with a little bit of impurity of nickel and a few other heavy elements. And this actually grows over time. Little by little, the mantle will fuse to the core. It goes through a phase change. The mantle has a good deal of iron in it, and it slowly settles on it, grows. This gives off some heat and helps keep the mantle hot. There's also some radioactive decay from various elements, but the growing of the core is part of the heat production of the planet. The heat of fusion being given off as more of that mantle settles onto the core solid. So we can see there's a giant difference in the concentrations of iron, as iron had just shifted to the lower levels of the planet. Nonetheless, there's still some on the surface, and we harvest billions of tons of it every year. It is a requirement to modern society to use iron for modern steel production. So various elements show up in different regions for different aspects of the growth of our planet and its development, from the initial accretion disk around the sun to the eventual planet that we live on today. Well, as all those processes occurred, as all the mixing of the elements that could mix together did so, they tended to react in various ways and end up in the more stable materials. And so on Earth, we tend to find various elements in particular types of material. Various elements in the early transition metals are really good at making oxides. If you are to find iron on the crust, you're going to find it as rust, Fe2O3. If you're going to find vanadium, it's going to be some vanadium oxide, titanium oxide. Same with pretty much all these other early transition metals. However, if you're a little later in the transition metal series, or even the metalloids, you tend to be found as sulfides. There's a balancing act between electronegativity and atomic size for why oxygen versus sulfur is favorable as a counterion. But the net effect is that these later transition metals and some metalloids tend to find in the form of sulfides. This is actually how we found one of the earliest metals humanity ever harnessed, mercury. Mercury sulfide is this beautiful red rock called cinnabar. And all you have to do to purify the mercury out of it is burn the rock. Oxygen and sulfur will react to make SO2, and you'll get mercury metal. So at some ancient point in the past, somebody with a fire pit put a beautiful red rock on it, lit some fire, it smelled a little funny all night, and in the morning, they noticed part of the rock had burned away, and there was a silver liquid in their fire pit. Other sulfides aren't quite as easy to collect, but nonetheless, this is how we tend to find these materials. Metal sulfides are notoriously insoluble, so anytime they found each other on the crust, they would make deposits, and if they were down in the mantles and things, then we don't find those deposits because we can't dig down that deep. But the material still tightly binds. They're very difficult to separate. If we look at the alkali metals and the alkali earth metals, we'll find that the sodium, potassium, rubidium, cesium tend to be found in the form of halide salts. These bond very nicely with fluorine, chlorine, bromine, and iodine, which is why we talk about sodium chlorides, potassium chlorides, sodium bromides, and the like so often. This is really the form that you're going to find them. They're very soluble in water, and so a great deal of it is in our ocean water. In fact, this is the primary source for iodide for folks, which is an essential micronutrient, and is part of the cause for goiter for inland communities in the ancient past. The reason we have iodinized salt these days is because it was really easy, while making salt from the ocean, to just include the iodine, a little extra, a little purified iodine added to your salt, to send inland with the food. Coastal communities tend to not have as big a problem. A diet of fish and things from the sea tend to contain enough extra iodine to avoid it, but inland, there just wasn't a significant amount of iodine in the local environment, and so lack of iodine could cause health problems. Well, the other alkali elements, the alkali earths, magnesium, calcium, strontium, barium, these tend to form carbonates and sulfates. The +2 charge of these cations and the nature of their size and electronegativity bonds quite well to carbonates and sulfates. This is why seashells exist and do not dissolve in water. A calcium carbonate, a seashell, or chalk, if it's been compressed through the ages of lots of seashells, is an insoluble material largely in water. You'd have to make it very acidic to get those carbonates to break down. And so this second column of the periodic table we tend to find as carbonates and sulfates. Once they bonded, they stuck together, were insoluble, and just remained that way within the Earth's crust. Some elements we don't tend to find combined, gold and platinum, nitrogen and oxygen these days in the form of O2, the noble gases. It is possible to find elemental sulfur, despite that it is used for many other things. Sulfur itself can also be found native in various places. And carbon, in various forms, due to life on Earth, can be found in no particular one setting more than any other. Because of the common sources, this means that if we want to refine some of these metals, we have to deal with them through processes designed to deal with whatever their counterions are. As I said with mercury sulfides, we can just burn it. And to a degree with some of the sulfides, that is the case. Just heat with oxygen. You'll make molten metal and you'll drive off SO2. That's a little bit harder with the oxides. They much prefer oxygen, and so we have to remove those oxygens. Later videos will go through some of the processes to actually refine these materials into their pure forms. But here's a handy graph to help us identify what forms we just expect these elements to be likely found in on Earth. None of this is perfect. There's a huge amount of the planet. There's a lot of variety. But if we're going to go search for them, these are largely what we'll tend to find them as in any mass concentrations.